Welcome to Summarize Science. Have you ever considered that a camera might not actually need a glass lens to work? Standard cameras use lenses to focus light, but researchers are developing lensless cameras that are much thinner and lighter. Instead of a lens, these cameras use a diffuser, which is essentially a material that scatters light into a giant blur across the sensor. On its own, this sensor data looks like complete static to the human eye. The real magic happens in the computer, which has to unscramble this multiplexed information to recreate the original scene. The researchers built a prototype called Diffuser Cam to test a new way of solving this puzzle. They used a simple piece of double-sided Scotch tape as the diffuser and a standard sensor to capture the light. To gather data, they displayed thousands of images from a natural scene dataset on a tablet and recorded how the light scrambled. The big problem with previous AI methods is that they were resolution dependent. This means if you train the AI on small images, it would completely fail if you tried to give it a larger, high-resolution image. To fix this, the researchers turned to something called Fourier Neural Operators, or FNOs. FNOs are special because they process information in Fourier space, which deals with the frequencies of light patterns rather than individual pixels. As seen in this architecture diagram, the system performs a series of mathematical transforms that naturally align with how light actually scatters. This approach treats the image as a continuous function rather than a fixed grid of dots. When they tested the FNO against a standard industry-leading AI called a UNet, the results were impressive. The FNO produced much sharper images with higher accuracy across various complex scenes. Even more surprisingly, the FNO was faster to train and used significantly less computer memory. The most mind-blowing part of the study is the resolution-agnostic capability. The researchers trained the AI exclusively on tiny 128 by 128 pixel images. Without any extra training, the same AI was able to reconstruct images at 256 and 512 pixels with almost no loss in quality. This is shown here, where the AI successfully fills in details it never saw during its training phase. Essentially, the AI learned the underlying physics of the camera rather than just memorizing patterns. This makes the system incredibly robust and adaptable to different types of hardware. The researchers suggest this framework could be directly applied to other fields like medical endoscopy. Imagine a medical probe as thin as a human hair that can still provide crystal-clear high-definition video from inside the body. By moving the heavy lifting from the physical lens to the digital processor, cameras can become smaller than we ever imagined. To recap, this paper shows that using Fourier math allows AI to handle light in a way that is faster, more accurate, and more flexible than traditional methods. In the future, this could lead to a world where high-quality cameras are embedded invisibly into everyday surfaces. It marks a significant shift from optical engineering to computational reconstruction. Thanks for watching Summarize Science, and stay curious about the tech shaping our future.